All right. Hello, everyone. How is it going? Thank you for the kind introduction. Well, I'm Pierre Lupi-Chen, data scientist, engineer, part of the R&D team of Realeyes. Okay. When I was a kid, I loved watching television, series, movies, cartoons, even geographic documentaries. Basically, I loved everything except Baywatch and those random, boring, mediocre commercials that make you channel hop as soon as they appear on your TV screen. And then I grew up. I was a teenager, found in US blockbusters, not at all in commercials, but still, nearly after 20 years, I can still remember some of them. Basically, the cult commercial for Lycos, a search engine long before the hegemony of Google, and the second one is the Indian Sculptor, a commercial for a French car, Peugeot 206. Without going into the details of those commercials, I can state that they do share some similarities. First, similarity that at that time I found them quite hilarious and very disruptive compared to the average, mediocre deluge of commercials. And the second similarity is that they both display some similar content on screen, like animals, but basically I'm not very fond in animals in itself. And then I grew up again. I was at university, and we had a very impressive seminar about disruption in advertising. What does that mean? Well, it means that you're trying to create such a powerful advertising message as to make your advertised product memorable in time by eliciting more emotions to the viewer than the average mediocre commercial, by engaging him a lot, even confusing him a lot. And from that perspective, we can view that the efficiency of an advertisement can be measured from two sides. From the brand side, a good ad is an ad that raises up its sales, its business outcomes, while from the buyer side, a good ad is the one that makes the product memorable, ultimately change his buying behavior by engaging him, by confusing him, in one word, by eliciting him some emotions, which is kind of my introduction to the topic of that presentation, how emotions drive business outcomes through advertisements. Realeyes, the company I'm working for, is one of the leading actors in the market research industry in terms of extracting emotions from videos and analyzing them with respect to business metrics. Our clients are diverse: brands, marketing agencies, medias. How does it work in a nutshell? Well, when clients come to us with 300 advertisements to test, we display each advertisement to a panel of buyer target audience carefully selected with respect to the demographic census imposed by our client: country, gender, age, and social metadata. While we are displaying each advertisement to the buyer target audience, meanwhile we record their faces through their desktops and mobile cams. Ultimately, we extract the emotional data from the recording and map such emotional data to our clients' advertisements' business outcomes through machine learning prediction models and its related business and creative insights. As for the R&D team in Realeyes is divided into two entities: the computer vision team and the data science team. The computer vision team is responsible for implementing, maintaining, and improving our core technology at Realeyes are emotional classifiers that extract emotions from the recordings. On the contrary, the data science team is more customer-focused, in charge of the data analytics, the machine learning predictions of business outcomes, and ultimately the reports of business and creative insights. About our core technology, we currently extract 3 main categories of emotions, of behavior cues. Facial expressions, happy, surprised, confused, and so on. Facial action units, eyebrow raise and furrow, and so on. But also various set poses, pitch, row, yaw. Here is the big picture of the pipeline of our emotional classifiers. The pipeline is divided into 3 parts: prerequisites, preprocessing, and modeling. The prerequisites involve 2 detectors. The face detector is built on a latent SVM classifier. The facial landmarks detector is built on a generalized linear model. As for the preprocessing steps, they are quite standard for the computer vision community. Facial landmarks alignment, face cropping around the facial landmarks, and ultimately data augmentation via random enrichment, rotation, scaling, shifting, and so on. Finally, the modeling. It involves an LSTM on top of a CNN. We do have 1 classifier for each emotion. In that sense, none of our classifiers' outputs are multivariate. Now, let's talk about the core of the topics, the data sciences. The data science team is customer-oriented. What does that mean? It means that we have to answer to 3 main questions from our clients. Is my commercial efficient? Which demographic to target with that commercial, and ultimately, how to improve my creative. First of all, the data science team has to face with some challenges. The first challenges are from the experimental design limitations. Usually, we collect emotional data for each advertisement only once, because collection is expensive. In that sense, data collection is kind of frozen in space and time, which can represent a caveat to make our predictive model and its related insights robust in time and generalized well. Furthermore, the experimental design does not take into account external factors like seasonality or economic effects. The second kind of challenges that we face with is a matter of machine learning itself. The type of learning task we have to deal with, namely aggregative learning task, is far from being standard. As a quick reminder, a standard supervised learning task is given by a data set in which each point is a pair of x and y, the x's being the predictor features, the y's the target variables to predict, and as we can see, there are as many y's than x's. On the contrary, an aggregative supervised learning task is given by the union of 2 data sets of different cardinalities. Usually, there are radically less y's than x's. However, there always exists a logical reasoning linking each point of target dataset y to a subset of points of predictor features x's. In that sense, this is always possible to aggregate the subset of predictor features points x's from its original level into a single predictor feature point lying on a coarser-grained level. To illustrate that fact, with our framework, when our client comes with 300 advertisements to test, the y's refer to the 300 business outcomes related to each advertisement, while the x's refer to the 100,000 participant sessions we collect for such task. Then an aggregative learning task implies two things. First, the need of a proper feature engineering in order to create predictor features point on the media level from the session level. And then second, that the sample size of your original data set is radically shrunk from 100,000 points on the session level to 300 points on the media level. Now, let's answer to the first question of our customer: is his commercial efficient from the buyer side? Here is the typical machine learning pipeline we are currently using at Realeyes to tackle an aggregative learning task. At first, the emotion time series are extracted automatically by our emotional classifiers. And then comes into action the data science team, basically within 4 parts: feature engineering, feature selection, modeling, and put the model into production. Part 1, the feature engineering. Any aggregative learning task needs feature engineering. As for us, we voluntarily put out of any training pipeline that feature engineering, meaning that we need to avoid any kind of data leakage. On the session level, we do have originally emotion time series. We currently have 2 ways of extracting features from those time series. The first one is a bottom-up, agnostic way, for instance, by detecting emotion events described by peaks, and then extracting the characteristics of those peaks. The second way is a top-down, domain knowledge way inspired by psychology and market research. For instance, market research is used to focusing on the first very seconds of an ad versus the last seconds. As for us, we need to engineer features taking into consideration the emotional lead deviation between the beginning and the end of the ad. Once we have extracted emotional features from the session level, we just have to aggregate them by a statistical way across the panel of all sessions having watched the same video, the same advertisement. It results in a single multidimensional predictor feature point lying on the media level. 1 point for 1 advertisement, 300 advertisements, 300 points. At that stage, we overcome the limitations of the experimental design and the aggregated learning task by bootstrapping the original panel of sessions per advertisement 100 times. It results in 100 more points per advertisement. Those points are all different between each other and also from the true value point. These are like altered duplicates synthetically created by bootstrapping. It results in 30,000 points on the media level then that we scaffold in a stratified way. 80% go to the training, 20 to the harder set with 2 specificities that for the harder set we basically drop all the bootstrap duplicates and we take care that none of the advertisement present in the harder set have any point in the training set. Part 2, the feature selection. The feature selection is basically working in a funnel approach. This is the first part wrapped up in the training pipeline. It's cross-validated during an hyperparameter optimization procedure. The feature selection has 3 steps. The first one is very standard. This is a simple filtering based on some univariate statistics. You can also add bivariate statistics, basically variance, entropy, multiple correlations, and information metrics. The second step is an adversarial validation. The adversarial validation is a technique enabling to distinguish a subset of features which do not exhibit similar patterns across different arbitrary splits of your dataset. If such features do exist, whatever the task you want to learn, those features will not be informative, and the best case scenario is that they will just make your best model's performance suboptimal. So you need to filter out such features. The third step is a conventional one, selecting features based on their importances and effects. Both the second and third steps need various models to train in parallel. As for us, we use ensemble of decision trees, random forest, extremely randomized trees, adder boost, XGBoost, gradient boosting trees, but also linear SVMs, generalized linear models, and multinomial naive Bayes. All of those models need to keep the ability to track back the importances and effects of the original features. In that perspective, we need to avoid to apply any kind of feature preprocessing step combining the initial features all together, like matrix decomposition and other dimensionality reduction techniques. Finally, all of those models have various hyperparameters to optimize. Part 3 is the modeling. At that stage, we extend our initial list of models to train in parallel, ensemble of decision trees, generalized linear models, discriminant analysis, both linear and quadratic, nearest neighbors, naive Bayes, multinomial Gaussian Bernoulli, but also kernel methods, SVMs with different kernels, linear, Gaussian, polynomial, radial basis, and so on, but also kernel-rich, kernel-logistic regression. At that stage, we also enable various feature preprocessing routines, namely matrix decompositions, ICA, PCA, kernel PCA, robust PCA, truncated SVD, and so on, feature embedding via random forest, feature clustering, basically combining together highly correlated features, kernel approximation like the Nystrom sampling, and so on. All of those models, trained in parallel, including their preprocessing steps, have various hyperparameters to optimize. Basically, we tune them jointly to the ones of the previous part, feature selection, via a Bayesian optimization using random forest-based SMAC model. We do prefer this model to the well-known 3000 estimator, TPE, and other Gaussian process models. Once we have all of those models, we just have to make a selection of a subset of models in order to aggregate them into an ensemble, into a blender. Why doing so? Because we do not want to select only one model. When you select only one model, you commit yourself with only one single hyperparameter setting and the high risk to overfit. Which model should we combine? Well, the ones exhibiting the best cross-validated performances. But meanwhile, we always have to check if the errors are non-correlated. And finally, how to combine them? Well, there are various routines. Stacking, gradient-free optimization. As for us, we prefer another one, ensemble selection, which is a greedy procedure beginning from an empty ensemble, adding only one model at a time, aggregating with uniform weight, but allowing for replacement of model for repetitions, and just judging if the model just added is worth keeping or dropping based on the ensemble validation performance. Part 4, and last part of the pipeline, put the model into production. Here, we have selected our best models, aggregated them in an ensemble. The Bayesian optimization has found more or less optimal hyperparameter settings. We have tested the entire thing, the overall, on our ordered set. The test performance is fine. We freeze the hyperparameters. We just want to retrain the ensemble of best models on all the full data available. The only question that remains is which full data available? Maybe only the true valued points, the 300 points, or should we also include the bootstrap duplicates, resulting in 30,000 points? Well, honestly, I have no strict answer to that question, but just an advice. If you want to retrain on the small data set 300 points, you need in prior to restrict by severe boundaries your hyperparameter space that the Bayesian optimization explores. Because you do not want that your ensemble of Bayes models originally trained on a large data set suddenly overfit when retrained on a smaller data set whose sample size is basically twice less in order of magnitude. Now, let's answer to the two last questions of our customer. Which demographic to target, and can we improve this creative? One specificity that I didn't mention earlier is that we do train, during the modeling part, a specific ensemble of decision trees, namely a rule-fit classifier. The rule-fit classifier is basically a very simple combination of a gradient boosting trees plus a lasso regression, and its particularity is to infer a set of decision rules that we currently use as insight for our customer. Then, given a combination of a specific demographic and a specific creative content can be content displayed during the advertisement, like people laughing, pet on screen, branding, production, etc. We re-engineer the emotion features points for each advertisement. We do not bootstrap anymore. The emotional impact of the combination of the demographic plus the creative content with respect to maximize the business outcomes is then accessed via the number of insights, the numbers of decision rules that the newly re-engineered emotional feature point set does check. In that way, we can basically rank the combination of best demographics and creative content to maximize the business outcomes and ultimately answer our customers' two last questions, stating on which demographic our customers' advertisements elicit the best, the right emotional responses, maximizing its business outcomes, and which creative contents do elicit such right, proper emotional responses. Last but not least, I have listed two directions that we are currently taking in order to engineer new features. From time series analysis, anything related to auto regression, moving average, etc. But also from topological data analysis, particularly speaking about silhouettes, for instance. Thank you for your time, and thank you for your attention.
Thank you for the exciting talk, and we have some exciting questions for you. How well would the algorithm work with Estonians? At least 25 people are interested to know.
Yeah, I think we are talking about the emotional classifiers. Well, basically I have no clue. Sorry. I do not know. But I do think that I think they work as fine as for European faces and North American faces. Our main issue usually, today is with Chinese faces because they do not elicit the same kind of emotions as Europeans and North Americans.
Is it possible to distinguish between natural emotions and intentional, made-up grimaces made to fool the algorithm?
I do not think so. But basically, I do not think that this is our main issue, for us, because the participants of the panel by our target audience usually do not try to fool us at all. If they're bored, they just go away from the camera.
Let's imagine that Apple unlocks iPhone Face ID. What would you do with that?
Unlock
Yeah. Disclose
iPhone
this.
Face ID. Well, as an evasive answer, I do not have such a version of my iPhone. I have an old one. But I do think that it would be a great opportunity for everyone in the facial recognition industry to then work at least with Apple if they allow it.
People are asking you to show your product in action. Is it possible?
It could have been if I was asked before, but right now I cannot. I can ask. Last year we were in Cebit, and we had a production. Basically, we called that the emotion mirror, and it was the main attraction of the stand of booth from the European Commission. Everyone coming and seeing themselves in front of the mirror and the televisions, the TV screens, and basically that toy example in real time showed them different kinds of emotions elicited with different intensity levels. Yeah.
Still, there is another motivation to join us in the after party.
Yeah, but I already have a good one.
Yes, there is an interesting question from Dairo again. What are the KPIs of your computer vision and data science team? How you measure their efficiency?
Well, I know my personal KPIs, but I would say that we do not set KPIs about our product, but we set the KPIs as teams. However, the main KPI of the computer vision team is basically to improve the current technology, to have better accuracy. Basically, we do not measure accuracy, we measure Matthew's correlation coefficient. To have a better MCC for all the kind of emotions, to also implement new algorithms, new classifiers on different emotions. And as for the data science team, the best KPIs is to basically have a great accuracy, a great MCC on our predictions for any client.
Thank you.
Thanks all.